Welcome everybody to this new seminar of the NA-GROM series. Today with us we have Kathrin Smetana, and she will talk about model reduction for seismic applications. So thank you, Kathrin, the floor is yours.
Thank you, Maria, for the nice introduction, and thanks to the organizing team for inviting me. And thanks to all of you who are listening for coming to attend. So this is joint work with the PhD student Hamza Khalid, who's mainly done most of the work here, Reese Hawkins, who was a postdoc on the project, and Matthias Stadtbrom from the University of Twente. Just one question, can you hear me, understand me well, or should I talk louder? Is that fine?
I can hear you perfectly, actually, so you can go.
Okay, perfect. Thank you. I don't have to screen then. So here are pictures like from, as I said, Hamza did most of the work, and he's finishing up the paper at the moment. And actually the thing I'm speaking about today is part of a larger collaborative project. And here we have like a picture of a Zoom meeting, which we had still during the pandemic. And so the whole team is led by Juno Trampert from Utrecht University, who's a seismologist, and Hanneke Paulsen is also a seismologist, and Marie-Colette van Nieshout, she's specialized in stochastic problems. And I want also acknowledge funding from NWO and specifically the DeepNL program. So the motivation for our collaborative project was that within the area of Groningen in the Netherlands, gas production led to subsidence and seismicity. So on the right-hand side, you can see a lot of these yellow dots where earthquakes occurred. And obviously this has been very stressful for the people living there. So basically, they had this DeepNL program to find new models and also to make, for instance, predictions depending on the gas production on how much seismicity we'll have. And that's actually one of the goals of this collaborative project. So one is that we want to do full waveform inversion. That means we want to provide a detailed picture of the 3D structure and the velocities in Groningen. So that just basically means you do solve an inverse problem where you try to minimize the error between actual seismograms that you record and synthetic seismograms. Then we wanted to develop a monitoring tool. That means that every time, for instance, we have an earthquake, then we can sort of rerun everything and get precise information on how the elastic structure and the velocities in the subsurface changed. And the idea was to do that with neural networks. And finally, this was what I just mentioned, to develop statistical models of the latent earthquake risk. And that can then be used to, for instance, also influence extraction policy. So how much gas should be extracted or not. As you can see here on the left, here you can see part of a 3D plot of the respective simulations. So the problem is, well, it's an inverse problem, so very many forward simulations are needed for full waveform inversion and also for the training of the neural networks. And the issue is with many of these seismic applications, very easily the size of the linear system that you have to solve really at the end is in the billions. And obviously that is computationally challenging. So even on the supercomputers and very good supercomputers, full waveform inversion for certain areas is just not possible. So the idea was here, I believe for the first time, to use model order reduction to really speed up the computations, to really make these full waveform inversion problems possible for certain areas. And as many of you know, because it's a model order reduction seminar, so I'm not spending vast amount of time there. So reducibility of wave time problems can be an issue, as is stability. So if you consider, for instance, a simple advection problem like that, then if you have here the initial conditions on the left, and then if they traverse forward in time, so you see several solution instances at different times, well, then it can be a problem, or in this case is a problem, to really find a good reduced space that works for the whole time, because as you can see, well, linear interpolation will not give in general a good result. However, what I really, really want to highlight here is that it's really a may. So in this case, we have not non-smooth initial conditions. However, as has been shown in this recent preprint by Kathrin and his students, that really the homograph n width of decay really depends on the data. So to the best of my knowledge, there's not a corresponding work for the wave equation, but also our results indicate that one would expect something similar, and also from the paper from Carson and his students, I think one would expect something similar there. But also for the wave equation, if you have non-smooth data, then what has been shown in this paper by Kathrin, then you can have a homograph and its decay that is as low as n to the power of -1/2. However, if you have smoother data, that really does not have to be the case. And in our case, we can actually show that we have an exponentially decaying homograph n width. And then also stability can be an issue because POD, for instance, might not yield a stable reduced model over time. So of course, we're really not the first people to look at these problems. So what has been done so far, people, for instance, suggested to use certain transformations, for instance, to align the shocks and then to reduce there, use neural networks, or work in the frequency domain, which is of course also something where you have to be careful because obviously it's a one-to-one map if you go to the frequency domain. So a priori that doesn't help you so much, only if you do some additional work there. And then regarding stability, one can of course, for instance, choose quasi-optimal pair of test and ansatz spaces, such that the ansatz space is chosen to give a good approximation and the test space is chosen to stabilize the problem. Or people also looked at symplectic model order reduction or more generally structure preserving approximations. So our approach here was that we wanted to transform the problem to the frequency domain. And then what we exploit there, and that's the main reason why we transform the problem to the frequency domain in the first place, we know that for the applications we're considering, the seismograms, they are band limited or low pass filtered. So they either might be band limited from the beginning or people low pass filter them on purpose. The reasons for doing that is, for instance, that if you include higher frequencies, then what's happening often is that the inverse problem solver for full waveforming version gets stuck in lower minima. So filtering out these higher frequencies is also really helping, for instance, in terms of full waveform reversion, which is one of the reasons why people in seismology really generally look at these band limited or low pass filtered seismograms. So if we're now in the frequency domain, the idea is really to exploit that because we're only interested in the low frequency range, that we try to stick to the low frequency range from the beginning to the very end. And I'll speak in a minute on how we do that in detail. I just wanted to highlight, so this is really actual recording from Croning. And if you look here, you see, so this on the right-hand side, this low pass filter is 25 Hertz, but you already see that the majority on the information and the energy is there until maybe like 15 Hertz or something like that. So really doing this low pass filtering is sort of a thing that does make sense and is consistent with the data one can observe. So what are the advantages of going to the frequency domain, as I just said? So we first get an elliptic problem, which is amenable to reduction. However, again, I really want to highlight here, and that's the next point, it's only because we can avoid the 5 frequency range. We know we have output of interest, quantity of interest and output, which is in the low frequency range. So what you see, what we're going to do is we select a source function which is already also limited to the low frequency range, we can then show that the solution is in this low frequency range and hence the seismogram is in this low frequency range. So everything stays there. And then we can build a reduced order model, which really allows to have a relatively small amount of basis functions, but still gives a very accurate approximation. If we would not know that we can avoid the high frequency range, well, it's one-to-one map. So if you don't do that, then it's not really clear how you could gain there. If you do need to approximate the high frequencies, well, then you obviously also need to have a high dimensional RB space there. I'm just emphasizing it because I don't want to oversell the method. So if we would need to approximate the high frequencies at the very end, we would likely also need a large model order reduction space. And because we're only interested in the solution evaluated at the receiver locations, the seismograms, we really don't need to approximate the whole wave field well, which is also helping. And the idea is really to build a model order reduction approach that is specifically targeted to this challenging application. And there are other applications where it might work, for instance, like structural health monitoring. We have, for instance, some damping. So it can also work in other approaches, but here want to specifically focus on the application that we had in mind here. So I'm starting with the problem setting, which is seismic wave propagation. So where we look at seismic wave propagation, as already said, we consider two parameters, the LME parameters, but we're also working on another paper where as an additional parameter, we're going to consider the location of the source, which also works reasonably well, such that you can really get a reduced model that works well for different source locations, which is, for instance, of interest if you think of early warnings of earthquakes, so get a really fast response where your wave field will affect how your wave field will affect certain areas. Then we look for a displacement vector. If we have homogeneous Neumann boundary conditions on the side and on the top, and homogeneous Dirichlet boundary conditions on the bottom. I just want to also to mention here. So the issue with these boundary conditions is so we choose them for simplicity. It's clear that they can cause reflections. So what we do basically, we basically have a larger domain and then we prescribe boundary conditions so that we sort of reduce the effect of the reflections. But in the next step, so we're looking at absorbing boundary conditions, which are the ones you would typically use. Then we assume that the medium is isotropic and piecewise homogeneous and under plane strain for 2 dimensions. And then we get the usual fourth order stiffness transfer. And I wanted to spend a couple of minutes to talk specifically about the source. So we take a point source located at a specific location within our domain. And then we take the Ricker wavelet, which is a standard choice in seismology, in time. And here you see, and below you see pictures for the Ricker wavelet for different widths. And you see that the higher the widths, the higher the gradients. And what we'll see later is that basically the higher the gradients and the higher the width, the larger the frequency range that we need to consider. And this is really nice because this alpha then allows us to really basically tune the frequency range to the seismograms, to the frequency content in the seismograms that we're interested in. So really have control over the frequency range from the beginning till the end. Then we denote by this set I, we denote the seismograms in the time domain, and they're just standard bounded linear functionals evaluating the solution at the top. So on the left here, you see a model of the crowning area of the subsurface. And generally, it's known there that the earthquakes generally occur in the sandstone layer there. So you have some prior knowledge where these earthquakes happen. What's particularly challenging that on the top you have the sediment, that basically behaves like pudding. So really, if you have an earthquake, then at the end, the top makes things very, very worse. And you really need a very fine discretization there to really resolve the waves that you get up there very well, because of the type of the layer that you have there. And then you get, for instance, seismograms that you see here on the right. So these are synthetic ones. And then, as already indicated, we transform everything to the frequency domain, and here we use the Laplace transformation. And what happens to the source? So with the source, we directly see what I said earlier. So the higher the width, the larger the frequency range really you need to look at. You clearly see for the green one that it's larger than for the other ones. And this is the reason, sorry, let me go back. So, but also you see it goes to zero very quickly. Actually, it goes exponentially fast to machine precision. So that also merits to really say, okay, we can really restrict our considerations to a frequency range of interest with some maximum frequency as max. And then we restrict ourselves to these frequencies. And then we also get, of course, the frequency domain seismograms down there. I just wanted to quickly say a few words about the variational formulation. So first thing is, what is really nice is compared to using, for instance, the Fourier transformation is that here, as you will see in a moment, you really get a problem which is uniformly well posed in S. So we do not have the challenges of a Helmholtz problems where we have areas where the problem is not well posed. So this problem is uniformly insubstable for all S and all M, of course. And in particularly, what we also have, so we get lower bounds for these Sub constants, which are very easy calculatable. So we have to solve once like this problem here, which is this beta b is the constant in Korn's inequality, and it's a lower bound for all parameters. So we calculate that once. And if you have that and you can do that offline once and forever, then all the other terms in there, they're really very easy calculable. See, it's just this constant here, which really depends just on the value of the parameter. So there is no eigenvalue problem that you need to solve online, which is really nice in terms of computations. And so this subconstant is actually, the bound is actually quite a good one. So it's not like really underestimating things terribly. It's astonishingly accurate. And here I also want to highlight in the continuity condition, you really observe what I said earlier. And again, I want to highlight that because I really don't want to oversell the method. You really see in there that you have the continuity constant depends on S max squared. So if you go to the higher frequency, you lose, as expected, you lose well-postedness, or it becomes more and more challenging. And then you have the stability constant, which depends on the maximum frequency range, and then you run in a lot of troubles in a lot of situations. And then you get the corresponding finite element approximation. Just one thing, what I want to highlight is that's, I think, is very commonly known for people who have worked at some point with complex valued functions. So, well, you can, of course, split the approximation into real part and imaginary part, and then you get this type of system for your finite element approximation. I'm just mentioning that here because we will later need that for the POD. But I assume that's really well known that you have this precise structure. So by doing that, we get our approximation in the frequency area, but we're actually really interested in the time domain seismograms. And we use Week's method to reconstruct time domain seismograms, which is using this expansion in the Laguerre polynomials. And you see here the coefficients AP, they depend on the seismograms via this term. So you have this infinite sum, and then you evaluate the seismograms and specifically frequency values, which are given like this. And again here, we're restricting ourselves to specific frequency range of interest, because otherwise you get a sum here that becomes very large, and this whole methodology also becomes really expensive. So there is actually really this connection between having a good reconstruction here, and then for the very same reason you also get a reduced base approximation, which is accurate even for small dimensions. And I wanted to put some plots here. So you really see here, these are the Ricker wavelets depending on the S parameter, so the frequency, and you really see the higher the width, the more frequency range you have, as we already had. But it's even more impressive here is you really see so the dark blue, dark red, and dark green. These are is the energy of your solution, of your wave field. And you really see that this energy of the wave field follows the source curve perfectly. So you really are able to tune the energy in your wave field by looking at your source term. And that means you really can control the frequency content in your solution, hence the seismograms. And also in some sense the other way around, if you knew that you need that you know the frequency range you're interested in the seismogram, you know approximately how you can choose the alpha in your source. And then of course the smaller you can choose your alpha, the better, because as you can imagine, and as you will see shortly in numerical experiments, the larger the frequency range, the larger the number of basis functions you need to get reduced basis functions you need to get a good approximation. And we also compared it with this numeric beta method time scaling scheme, which is the usual method people use for these type of problems. And this is again the relative error in the seismograms in time. And what you see here is again this S-max parameter, which determines our frequency range of interest. And you clearly see that you have a very, very fast decay of the error in the seismograms for S-max. So here, this really tells you how, well, that we're not committing into a large error by restricting ourselves to the frequency range of interest. So how can we exploit these features for model order reduction? So first, I wanted to speak about the reduced model, and specifically here, the exponential decay of the Kolmogorov N-width. So we've had one paper where we looked at model order reduction mostly via eigenfunctions, and as already mentioned, so Hamza at the moment is writing up the paper for what on the results I'm presenting here today. So what we have here is if our parameter m is fixed, and then we take some s parameter value, which is convex valued, then we get that the Kolmogorov N-width decays exponentially in the number of basis functions you need. And what you see here is that this depends again on S-max. That means, of course, the larger S-max is, so the larger your frequency range of interest, then at some point the exponential decay becomes very, very small. And also here, the C hat, it depends like 1 over S max. So also here, the constant, the larger S max, oh, sorry, the other way around. It's S max divided by SR, and the larger S max gets, the larger also the constant becomes in front of the exponential. Then I want you to come to the construction of reduced basis methods for fixed M. Just wanted to briefly recall the find element approximation. Again, as I said, you have the structure here where you have the real parts diagonal, and then you have the imaginary parts on the off diagonal. And then it has been suggested on several occasions to use, like, for instance, just correspondingly PUD, which is convex valued. So basically, this is just PUD straightforward, just accounting for the fact that you have complex valued numbers. And that's what we used here. Also, some people suggested to use, in this case, like symplectic POD via codec and lift. If you're familiar with symplectic methods, you might recognize that actually the structure that you have here actually really, if your reduced basis is orthonormal, that you actually have here a symplectic structure, which is not surprising given that we do Galerkin. And then yeah, we actually compared the two, and at least for the problem that we're considering with these layers, really the standard complex valued POD really outperformed symplectic POD significantly. You see specifically on the right, you see like the error in the seismograms. So in the lighter color is the complex valued POD, and the darker color is the symplectic POD, and you really see a huge difference between the two. I would also like to mention, out of fairness, we also had considered a problem at the beginning where we had like a homogeneous medium, and there they performed similarly. But for the heterogeneous problem, we really see a huge difference. And then we also considered the greedy algorithm, and here the greedy algorithm is driven by an error estimator for the error in the frequency domain seismograms. Oops, sorry. Now I wanted to speak more about the a posteriori error estimator. As I indicated earlier, so we have those lower bounds for the soup constant. They're not so great because they still depend on the, as you can see up here, they depend here on the norm. So this norm is parameter dependent. That's an easy fix, of course, to get here norms that do not depend on the parameter. And then you get a slightly different constant, but still very easily calculable, as you see here. So basically, you only need this SI parameter and S max. And then the C1, C2 constant, they such as norm equivalent. And then, well, you get your lower bound. And then we get the usual a posteriori error estimator for the error in the frequency domain of the wave field. And then the effective expectivity is bounded as usual by the continuity constant divided by the M sub. And again, you see also here, as expected, the continuity constant grows quadratically in S max. So also the effectivity of the error estimator, of course, gets really bad if you need to go to higher frequencies. So this was the error estimator for the frequency domain, which is really standard. But the nice thing is, so we can use this frequency range a posteriori error estimator to derive an error estimator for the time domain seismograms. So I'm just recalling here the reconstruction method we used for Week's method. So we replace basically the seismograms here in this coefficient by the error. So the error between the fine element seismogram and the corresponding reduced seismogram. And then you simply estimate this error by the frequency domain error estimator to get an error estimator for the frequency for the time domain seismograms. And that's what we did here. So basically here you have your error estimator for the frequency domain time domain, and you have the sum that comes from Week's method. Here we used just the dual norm of bounded linear functionals. Of course, if you would use a primal dual a posteriori estimate, we're aware that this would give better effectivities. But for our purpose, this was perfectly sufficient. In the a posteriori estimator was reasonably sharp, and in particular, the convergence really nicely followed the true error. So we didn't go the lengths of using a dual problem here because it wasn't necessary for these circumstances. And I want to highlight here, as I said, so we will never really we never need to really solve the time domain problem, but we still can design algorithms to construct reduced order models that that are driven by our estimators for quantities in the time domain. Works precisely exactly the quantities we're interested in, the time domain seismograms. Then I wanted to come to goal-oriented parameter model reduction. So we have been investigating two algorithms there. So we use always a greedy algorithm for the parameter, which is chosen such that it maximizes the error estimator for the error in this time domain seismograms. And then we use either a POD greedy in the frequency domain, meaning that we apply a POD to the projections error in the frequency domain. So this POD greedy mimics the POD greedy in time domain by Hausdorff and Ohlberger. Or we use also for the frequencies a greedy algorithm. And what we saw in the numerical experiment that they both, well, perform very similar. So both were basically doing more or less the same. And now I'm coming to the numerical results. So as I already indicated at the beginning, because if you choose, well, homogeneous Lyman boundary conditions, you get reflections, basically extended the model domain to the left, to the right, and to the bottom, and then to very much reduce the influence of the reflections. And then we choose a Gaussian point source in the fourth layer, which you see here, this one up here. And the receiver locations are well positioned on the top. And we compared with an implicit numeric beta method. And so first I wanted to start with the picture of the error in the seismograms and all the seismograms itself. So what you see here from the left to the right is the width in the Ricker wavelet, so the width on the source increases. And what is nice to see on the left, you see seismograms, but then if you go to the right, these are the same seismograms, except that they have an increased frequency content. You really see, hopefully, that there really is some similarity. And the higher you increase the width, the more frequency content you get. But for all of these, we get really nice approximations with the reduced order method. And here we fix the parameter m to the parameters that you see here in the layers. And you also see that, so on the left, the reduced order model has a dimension of 76. In the middle, it's 126, and on the right, it's 167. So you really need, as expected, a much larger reduced basis method if you increase the width according to the frequency content. But it's still moderate. And accordingly also, and really not surprising, you also see that dependency of the singular values on the width of the Ricker wavelet, and of course the decay is slower and slower the higher the width is, the higher the frequency range. And then you see here in the middle, you see the convergence of the greedy algorithm. You use the error estimator, or on the right, you use the convergence of the greedy algorithm. You use the true error in the seismograms. And you see, well, the error estimator overestimates the error to some extent, but in principle, the convergence is very similar. And so this is the convergence of the reduced model if you do look at the convergence over a test set. So if you want to say it like in the online phase, and you see here that, well, the POD and the greedy algorithm, well, they perform very similar. If you use here you see in the middle, you use the true error in the seismograms. And here on the right-hand side, I use the error in the time domain. So here on the left and on the middle, you use the frequency domain, and on the right, you use the time domain. And as already indicated, for the error estimator, so in the middle, you see the effectivity of the error estimator, and well, you really see it in red here. So there is some overestimation, but it's like the order 100, and it really see it nicely is constant. So you basically can't account for that by variation of the tolerance. And so here we varied the Lamé parameters, the same in all layers. So we basically didn't consider them like independent, that we just chose them arbitrarily, because that would yield already a very large parameter space, but we did that later as well. So this is just if you add some random number in all layers. And what you observe here on the left and on the right is that the convergence of the POD greedy algorithm, the greedy algorithm is very similar. And also what you see here, so that's the online phase, where you also see that they perform nearly the same. And again, you see that we nicely approximate the seismograph. And then we really chose the parameters in the 5 different layers arbitrarily. And then we looked at the influence of the change. So you see like 5% change or 10% change. And the idea is here why we looked at these variations, having, for instance, already in mind that we want to use that within full waveform aversion, where we maybe want to keep the reduced model from one iteration to the next iteration in the inverse problem solver, and not recompute the reduced or adapt to reduced model in every iteration, but maybe only in few. And we expected, we see, well, the percentage of the change has quite a significant influence, but still with a decent amount of reduced order models, we still get a very good approximation. Just take time. Okay. Let me just, so because I still have, I think, 2 minutes. So quickly, so here what we also investigated are the wall clock time comparison, and what I want you to highlight here. So what we did compare here also is like the greedy algorithm with a POD for different processors, because typically, as I said, these problems are run on supercomputers. So if you do have, while thinking of HPC, if you really have a very many amount of processors, then this really is a nice way of getting a then you really can get a approximation for one instance only for the so for fixed parameter m. If you compare with the Newark beta method and add all the computational costs for the reduced order model, this can actually really be quicker in constructing reduced order model by POD if you have very many processors, and then run the reduced order model, and then do the reconstruction in time, compared to Newark beta time stepping scheme, which just runs once forward. So it's one way. It's not really, of course, not parallel in time computations, but it's one way to look at problems where we have the issue that really the time marching scheme is the reason why these methods, why the problems take such a long time to simulate. So here, that might be an appealing way to really say, okay, we use a POD on very many processors, and then the time for constructing the reduced model, the true wall clock time really goes down. And then we run the reduced model, reconstruct in time, and then get really decent wall clock time compared with Newark beta. So let me come to the summary. So as I said, so we transformed the problem to the frequency domain via the Laplace transformation, and the crucial point here was that our seismograms are already band limited or low pass filtered, And that really means we can restrict ourselves to the low frequency domain, because, as we saw throughout the talk, we can tune the width of our source such that the energy in our solution and also in our seismograms is limited to the area we're interested in. And then we have an elliptic problem, which we see actually yielded an exponentially decaying Kolmogorov N width. And because we can avoid the high frequency range, we really get a nice decay and small reduced basis, but still get a good approximation. And as I said, also the evaluation also only at the top. In generally, we would expect it helps, and it does, for instance, for the homogeneous problem, but not so much for the heterogeneous problems. It seems like because the problem is so, because of the different layers, cause so many interactions, that it really seems like that you really don't gain too much by only looking at the quantity of interest compared to the whole wave fields. So we compared a lot, and we're really thinking a lot of why it's not helping so much, but it really seems that only if you only change, for instance, the source location by a little or the parameters by a little, already the wave fields look so different that also that affects more than just yeah. So you basically, if you have two wave fields, you don't get the symmetries one might hope to get as we see seismograms, that they're nearly the same even for two different wave fields. It doesn't seem to happen. The wave fields themselves are already very different. So that doesn't help too much, except if you look for very simple problems. But the other 2 points do help a lot. And then, of course, we really try to have this POD greedy algorithm or greedy algorithm targeted at the time domain seismograms, or if seismologists are interested also in the frequency time domain, So thank you very much for your attention, and I'm very happy to answer your questions.
Thank you, Kathrin, for this very nice talk. So now it's question time. As usual, if you want, you can unmute yourself and ask directly Kathrin your question. So let me see if there are questions. Oh, yes, Trajan, go ahead.
All right, so very nice talk, Kathrin. I mean, really enjoyed it. So, because it's a different point of view, I think that's a different take on different type of system. And my question is, I don't quite understand very well all the details, but because this is not what I'm doing. But so you did say one important part of your talk was about restricting your attention to a certain bandwidth, right? I think that this is very important, and so my question is, do you have like an algorithm to determine what the right bandwidth would be? Like I remember you said something about the 15 hertz frequency, and I guess what I'm asking is, if somehow you don't choose the right frequency domain at the beginning, could you think about doing something in the online stage? Because to me, restricting the bandwidth is equivalent to filtering. And I'm thinking...
Absolutely right, yes.
Right. So I'm thinking, if you don't do right, that's exactly the slide. So if you don't do the right thing, let's say that, where you don't have the right amount of filtering at in the offline stage, would it make sense? Maybe not, I don't know, to look at something similar, maybe some sort of filtering at the online stage, or this is not needed at all? There's no need for additional, just a thought. I don't know. I mean, it's just...
It's a great question. Thank you so much. So let me just try to go. So I'm not aware of an algorithm on to select the right amount. But so what I understood from our collaborators were that they sort of know what to choose.
Mm-hmm.
But I'll ask them again. I think that's a great point. Because that would be nice if one has. But I think in this case, I think by just looking at the content, I think it's quite obvious where you need to filter.
Correct.
Yeah. Regard to your other questions, well, one thing, and so now I have to go to the other end of the talk again. That was not so wise. One sec.
That's okay.
Yeah. So that comes back to what I said earlier. So I think assume you wouldn't know that you assume you really would need to change because you didn't choose the right bandwidth. And if you have to choose a let's say bigger one, well then I think you just could run more additional simulations in that area. They're not too expensive though, because well, we don't have a time margin scheme and things like that. And if you have many processors, it can be actually done relatively quick. Then I think one could use these methods which allow for easy update of the POD basis. And then I think you could easily update your reduced model to the frequency range should that be necessary.
See. Okay, thank you. This is very nice, very nice talk once again. Thank you.
Thank you for the great question. That's really nice. I definitely want to follow up with our collaborators because that's something I think yeah, which is important, of course.
Are there other questions for Kathrin?
Yeah, I can ask another curiosity. So,
Go ahead, Francesco.
like I think it was on slide 25 or 26. You had a case in which the material properties were changing by 5 and 10%, right? Okay, yeah, maybe it was not. Yeah, it was this one. Yeah, 27. Sorry. So my curiosity would be, is it of interest not only to change the coefficient, but is it possible that those 5 bands that you were showing are not like their depth or their precise location are not identified properly? So maybe there needs to be maybe there is some uncertainty about that. And so would you consider this even more challenging than changing 5% or 10% the value themselves?
Sorry.
Yeah.
Absolutely, yes. So the reason why we didn't consider the application you mentioned is the following. So let me just go to that. Okay. So as I mentioned, so one thing that one could do also is like this varying the source location. But the issue is what you say. That really depends then on how much information you already have on the location of the layers. So we talked with that about our collaborators, of course. And so my concern was why I didn't want to have that in that paper, because I feel I wouldn't go that route precisely if you have that application. What I would do is I would use localized model order reduction and then adapt locally your reduced model to the different coefficients. For the simple reason that, well, as I said earlier, this discretization easily can have billions of degrees of freedom. That's sort of the standard that people from seismology are looking there. So even if you have some constants and some pre-knowledge of your coefficient function, we're talking here about a parameter space that has dimensions of millions at least, very least, very worst case, much more. So I wouldn't advertise using that route because I know I would guess it will not perform well at all, because how could you do a good a priori model order reduction space to approximate that? I don't think you can. So I think in that case, you would, what I think you would do is you have your inverse problem solver, and then maybe you pre-construct some very preliminary local reduced spaces, and then within the inverse problem solver, you would update your reduced spaces locally to account for changes in your coefficient function. However, the whole structure of that, what I presented today, like you go to the frequency domain, you use that you have like a restriction to a certain frequency area, all that still applies, and all that I think you can use and need to use. So that's why we sort of decided to first do this part and then build on top of that. But yes, you're absolutely right. That would be of interest, but I just don't think unless you have a lot of pre-knowledge where your location is approximately, I think it will be very hard to build a priori a reduced order model space that could approximate that well.
Great, thank you.
Thank you. So it looks to me that there are no other questions for Kathrin. So I think we can thank Kathrin once again for this very nice talk. So thank you, Kathrin.
Thank you all for listening.
And we see each other, I think, next Tuesday. Yes. And see you all next Tuesday. Thank you very much.
Thank you. Bye.
Kathrin, see you.
Thank you.